Good afternoon. Today we'll be learning about Le Chatelier's principle. Now, Le Chatelier's principle is primarily concerned with equilibrium, and it'd be very easy to get lost in the verbiage, so I actually want to take this out to a real-world example because that's kind of how I think about the application of Le Chatelier's principle. So let's say here you are, your stick figure plus your buddy. There you are. But also, there's a little wall right here, and then you could go through this door into the room to move about. Now right now, you're just standing around having a good time. System's in balance. However, let's say there's a change, and your friend's a bit of a weirdo, so he gets really close to you. Now it's kind of weird, there's a lot of pressure being put on you there. You might respond. And personally, I'd respond by just going right through the door, into that other room. You don't want his breath up in your face. So that's actually, believe it or not, Le Chatelier's principle. Le Chatelier's principle describes how systems react to different pressures being put on them and the corresponding shift trying to return back to equilibrium, because systems always prefer to stay in equilibrium. So put that more generically in chemical terms, let's just put some placeholder species here. A plus B forming some kind of AB complex. All very straightforward, and there's a lot of ways that this could change. So of concern to Le Chatelier's principle, there are four primary factors: concentration, temperature, pressure, and volume. So through this, let's demonstrate a change in concentration. Right now, stoichiometrically, you have a balanced system, 1 to 1, forming 1 of the combination. So let's say, all of a sudden, you double it. Well, now there's a whole new pressure being applied to the system. It's going to react and try to shift and return to normal. So 2 to 2 to 1 doesn't work. You need another 2 over here. That's what happens as it shifts from a pressure being applied to the left side where you add more reactant. That's pretty easy to understand. So let's look at something a little different. Let's use a real example here. We have hydrochloric acid plus sodium hydroxide forming water and normal everyday table salt. Well-known reaction. But this time, rather than adding on the left side, let's say we have some kind of strange setup that removes the water from this system. So we're actually subtracting from the right. What do you think will happen? Well, according to Le Chatelier's principle, it's actually going to respond the same exact way, and it's going to shift to the right to fill that gap that's been created. So that's concentration change. Let's talk about temperature. To do that, let's use CO2 plus 4H2 forming water and methane. Now, let's see. Yeah, there we go. Okay, this is actually called the Sabatier reaction, by the way. But anyway, in the real world, this is an endothermic reaction, where for it to go forward, you need to add temperature to the system. And that's an interesting point to bring up, because in regards to temperature in Le Chatelier's principle, it actually depends on the system itself. So with this system, we know that it's going to require a change in heat on the left side to go forward. So if you were to add that, it's going to shift that way. But let's just pretend that this is actually an exothermic reaction, and you still did the same thing. Le Chatelier's principle would actually predict that it goes to the other side, because depending on whether or not it's exothermic or endothermic, will determine what temperature does. So you have to pay attention to that because it's not as simple as concentration. So just remember you have to look for that, and that'll tell you which way the equilibrium will shift. And actually, I shouldn't have erased all that because this same formula is useful in talking about changes with pressure and volume. So let's draw this back up. Some methane on the right. Okay, so pressure and volume, those are interesting variables because you have to remember they're inversely correlated. An easy way to think about that, just use your hands. Pretend this is a gaseous system. You're gonna crush it and apply a lot of pressure. If you notice, the volume goes down when the pressure goes up. So they kind of work like that. And remember that when dealing with Le Chatelier's principle in systems, because that's a very big impact. So let's say we add pressure on the left side. These are all gases, so I should denote that, oops, forgot my H, with a G. It's actually a liquid. Okay, so if we were to increase the pressure on this side, it's going to shift this way, correct? Because you have more gas, more pressure, it's got to go somewhere and it's got to do something. So as that pressure increases, we should actually observe a corresponding decrease in volume. And so that's pretty straightforward, and you want to look at what's happening. However, it's not actually talking about the total pressure of the system when I'm talking about pressure and volume, because I'd like to bring up kind of a surprising counterexample. Let's say that for whatever reason, we have this system going on, and we decide to add helium gas to it. Now, what do you think will happen? Well, it seems like it should shift to the right, correct? Because we're adding more pressure. But it's not actually talking about the total pressure of the system in regards to Le Chatelier's principle. What we're concerned with is partial pressure. So though we might think we're just adding helium on this side, realistically that's not what's happening. You're actually adding helium to the whole deal. So the total pressure of the system did increase. However, the partial pressures going on between your reactants and products didn't actually change. So the presence of an inert gas like helium, the noble gas, one of many noble gases, doesn't actually impact the system. So definitely remember that, because a lot of people might try to trip you up by adding inert gases to the system. But remember, inert gases that don't participate in the reaction don't actually change the reaction. Now, there's kind of a similar related phenomenon that tripped me up too, and that's the presence of a catalyst. Now, this is actually the Sabatier reaction and works much better in the presence of a catalyst in the real world. So let's say you have a platinum catalyst added to this reaction. Now that'll speed it up. What do you think will happen? Well, my first instinct would be to say, well, we're gonna, it's gonna increase the amount over here because it's gonna help speed up this formation process. But you have to be careful because the catalyst actually impacts the rate of the entire system. So the entire system changes. There's no real pressure to respond to. It stays the same. Le Chatelier's principle says nothing changes. So, to review, 4 primary variables to watch out for when you're dealing with Le Chatelier's principle. You have changes, concentration. Try to stay on this side so you can see better. Changes in concentration, changes in temperature, and remember, what does that mean? Well, depends. Is it an endo reaction or is it an exo reaction? That'll determine which way it shifts. Concentration, remember, are we adding / subtracting? They're both equally important, yet they have opposite effects depending on where it's being added or subtracted from. And then remember pressure and volume. And just so you remember, because it's an important one, pressure goes up, volume goes down, or vice versa. And don't forget, catalysts and inert gas don't actually affect the reaction. Kind of surprising. But hopefully you understood all that. If not, feel free to ask me any more questions. Thank you for listening.